Welcome, this is Dr. Jed. Today we're going to actually calculate the derivative, the first really significant calculus concept since we did the limit. And we're going to do it using limits. So first we'll do a concept, then we'll do a notation, and we'll close actually with an example. One example I do will not substitute for you doing examples. It's easier to watch me than it is for you to do it yourself. But we'll do one so you can see how to sort of walk through it. So first off, what is the derivative? Well, it comes from the tangent line. And recall, if this black curve is your original function, the blue is the tangent line at that point A. So, zoom in. We already know that the function, if you zoom in enough, is approximately linear. It's got a local linearity to it. So, the blue is the tangent line. How do you find the tangent line? Well, you can find it by approximating using the secant line. Pick a second point on our curve, and the secant line goes through both of those. What is the secant line? Well, the slope of it, if this is the point A, f of A, that's our base point. It's right there. The next point is a little bit over. So if A is here, move over by a distance h. So this is going to be A plus h, comma, f of A plus h. What's the slope in between? We take rise over run, f of A plus h minus f of A, over A plus h minus A. That's right here. Now you can simplify the bottom. A plus h minus A is just h. But what's really more important is that the slope of the tangent line is approximately the slope of the secant line. Or more precisely, it's the limit of the slopes of the secant lines as h gets smaller. So it's the limit as h goes to 0 of the slope of the secant line. Now why did we spend time talking about the slope of the tangent line when we want to talk about the derivative? And the reason is because the slope of the tangent line is the derivative. That's the derivative. Look back here. The derivative is the slope, not necessarily the tangent line. It's the slope of the function at any given point. This has a lot of applications in a lot of different places, but that's what we're trying to find. The derivative is the slope of the tangent line. Now there's notations for this. Rather than saying slope of the tangent line every time, we can write df d over dx. That's one notation. That's the Leibniz notation. There's also the Newton notation, f prime of x. This right here means the same thing as that. And they're both this. This is algebraically what we're finding out. All you have to know right now is that the derivative, which this is the one we usually use, is this. So let's do an example. Find the derivative of f of x is x squared plus 3x minus 7. So this is the formula for finding the derivative. Notice this is a difference quotient. It's the limit of difference quotients as the bottom goes to 0. What do we plug in? Well, we've got an x plus h right here that goes into the function and pops out in those two places. So h goes in here. That bottom is still h. That's really easy. F of x plus h is going to be x plus h squared plus 3x plus h minus 7. Now that is wrong because I forgot to put parentheses. I want all of the x plus h to be squared. And I want all of it to be multiplied by 3. And then furthermore, all of this is f of x plus h, so it's good to put a big parentheses around it, although that particular parentheses is not necessary. I also want to subtract off f of x. F of x is literally this. But again, I want to subtract all of it off. I don't want to just subtract off the first bit, so I need parentheses. That step is the hardest step of the whole process. So if you can do that step, you've got it all. Let's try. Let's try to simplify now. There are more steps. So what do? X plus h squared is x plus h times x plus h. There are middle terms. Formulate out if you want. We get x squared plus 2xh plus h squared. Then plus 3x plus 3h minus 7. Then finishing off here, minus x squared minus 3x plus 7. If you do this right, there will be a lot of cancellations. Things that are added, things that are subtracted. For example, here's a 7, here's a minus 7. Here's a minus x squared, here's an x squared. Here is a minus 3x, and here's a positive 3x. Now, that's a lot of stuff I did, so let me rewrite with the things canceled. What do I have on top? 2xh plus h squared plus 3h, I think that's everything, yes? Divide by h. If you do this right, you will be able to divide everything by h. Now there are more complicated functions, like if it's involving a square root or 1 over x or something like that, where there may be some tricks you have to do. But for polynomials, if you do this right, everything should have an h in there. Now, we gotta be careful. Canceling this way was pluses and minuses. Canceling here is dividing. And it can be tricky, especially if there's many terms, and especially if you're in a hurry. Say you're taking a test and you only have a certain amount of time to finish this problem. You go in, okay, I can do it. You can make mistakes. So what I always do is I do this a little more formally, this particular step. I want to factor an h out. If I pull an h out of here, what do I have? 2x times that h. If I factor the h out of here, I have h, because it's h times h. And here, if I factor the h out, it's easy to say 2h. That's not what I want. If I pull the h out, I have a 3. Now you check. That's right, that's right, that's right. And now, with the h factored out, it's easy to cancel. Again, if you have time to think about it, this really makes a lot of sense. If you're rushed, it's an easy way to avoid some pitfalls. So what do I have? 2x plus h plus 3 over 1. Now, all of that was important because when h goes to 0, we had a 0 on the bottom, but we don't anymore. In terms of h, this is continuous, which means we can just plug 0 in. 2x plus 0 plus 3. Notice I'm plugging it in for h. I don't know what x is, but I don't need to, because that is the answer. The derivative is usually a formula, and in this case, the derivative of x squared plus 3x minus 7 is 2x plus 3. Until next time, this is Dr. J.